Lesson 5 is Introduction to Proofs, and section 5.1 is introducing two-column proofs, which two columns is just referring to the way that we structure the proofs. So there will be a left side and a right side. And the left side is where we write our statements, which statements are just facts that are specific to the problem. And then on the right side or the right column, we write the reasons or the justification. It's just the way we justify our statements using postulates, theorems, properties, or definitions. And then these rules down below are just a bunch of different properties that we can use to justify our statements. So all of these would be something that ended up in the reason side. And I would recommend like just kind of creating an ongoing list of these and adding to them, just like you would with like postulates. They can all go on the same list. They're all just going to be reasons that you may use for your proofs. So I'm just going to go through these pretty quickly. On the left side is the addition property of equality. So it says if A is equal to B, then A plus C is equal to B plus C. So basically like A and B are the same, like these would be the same value. So if I'm adding C to both sides, it's going to keep the equation balanced. And then the subtraction property of equality, so A is equal to B. If I have A minus C, that would be equivalent to B minus C. So same idea as the addition one, where A and B are equivalent, they're the same value. And then I'm subtracting the same number from both sides, so the equation is staying balanced. The multiplication property of equality, if A is equal to B, then A times C is equal to B times C. Same thing, A and B are the same, and I'm multiplying by the same number on each side, keeping the equation balanced. The division property of equality, so if A is equal to B and C cannot be 0, then A divided by C is equal to B divided by C. So A and B are the same value, they're equivalent. I'm dividing by the same number on each side, so it keeps the equation balanced. The only reason this one says like C cannot be equal to 0 is because we're dividing by C and we can't divide by 0. It gives us an undefined number. And then on the right side, the other properties of equality. So the first one, the transitive property of equality, says if A is equal to B and B is equal to C, then A must be equal to C. So if I have like these two values are the same, these two values are the same, then these two must be the same as well. So A must be equal to C. And then the next one, the substitution property of equality. So if A is equal to B, then A can be substituted for B into any equation. So if they're equivalent, I can substitute one in for the other without changing the overall value. The reflexive property of equality, it's just A is equal to B and B is equal to A. Pretty straightforward. And then the symmetric property of equality. So if A is equal to B, B is equal to A. The reflexive one is just kind of saying that these two values are equal, so we can kind of set them equal or write them as an equation. Okay, so this example is writing a two-column proof. So we're given the following information. We're given that AC is 7 units, and then I'll use a different color, AD is 13 units. And you can like label on this if you would like to. If you have it printed, or you could draw a number line like this and kind of label it that way. So let's see, AC is 7, and then AD is 13. And then we're asked to prove that CD is 6. So this little part right here is 6. And I know sometimes like it kind of feels like, okay, it's just kind of common sense. I can just subtract and get 6. But that's the tricky thing about proofs, is we're trying to write things in like a more academic way. So we really have to like prove each individual step. So we're going to start with our first statement, and most of the time, if not all the time, your first statement is just going to be stating the information that is given to you. So for statement number 1, we're given that AC is 7 units. So I'm going to write AC is equal to 7 units. And then the second piece of given information is that AD is 13 units. And then it was given to us, so for the reason we would just put given. And when you're writing these, you should create a table like this as well, so you can kind of fill it in and keep it organized. And you always want to number the statement number with the reason number to make sure that they go together. So even if like you were writing on line paper and it was all on the same line, you would want to number it just to make sure. Okay, and then for statement number 2, we can use what's called the ruler postulate to say that, okay, if I add, I'm going to erase some of this information. If I add AC to CD, I'll get that entire distance of AD. So I'll get this entire section right here. That's the ruler postulate. So kind of like if I take 2 individual segments and add them together, I get the entire segment. So we write that as AC plus CD. So AC, that was the one like in green, and then CD, that was the one in purple. And then if I add those together, I get the one in blue, which was AD. And the property that tells us that we can do that, or the postulate that tells us we can do that, is the ruler postulate. And this is why it's really helpful, even if you haven't done it yet, to kind of go back through the workbooks and make a note of any postulate or rule or property that you saw. Because I don't really expect you to like memorize every single one that's out there, but you do need to be able to access it somehow. So having a list would be really helpful. Okay, and then now technically we know AC. We know AC is 7 units, so I'm going to substitute 7 into where AC is. And then we also know that AD is 13 units, so I'm going to substitute that in there. So I'm just going to rewrite the equation, but with the actual numbers in there. So AC is 7 plus CD is equal to AD, which was 13. And I substituted something in, so I'm going to go up and I'm going to use the substitution property of equality that says if A is equal to B, then A can be substituted for B into any equation. So the reason for step 3 will be the substitution property of equality. And then from there, we can kind of just like solve this equation, kind of like how you would in algebra. So you don't necessarily need to write this on your proof, but for example, like if I was trying to solve this like an algebraic equation, I would just like subtract this little 7 right here. I would subtract this little 7 right here. And then this would give me CD is equal to 6. So again, I wouldn't like write this on your proof, but like if I subtract 7, that would cancel that out. And then 13, oops, sorry, that's supposed to be a minus 7. 13 minus 7 is 6. So we're solving it kind of like an algebraic equation. You just wouldn't like technically write it on your proof. If you needed to, you could write it off to the side or erase it. And then that's giving us the value of CD, which is 6. And we subtracted to get here. So we used the subtraction property of equality. That one was up here. It said if A is equal to B, then A minus C is equal to B minus C. So we're basically saying like, okay, these two sides are equal. So there's like the left side is A, the right side is B. And then if we just go ahead and like subtract the same thing from each side, then they're still going to be equal. So like what I have left is going to be equal as well. Okay, so this one was the subtraction property of equality. So that is it for 5.1. That was our first proof of the year. We'll have to write more. I know they're not always the most fun thing, but try to think of them as like a puzzle where we have to put all the correct pieces together to end up at like our final fact that we're trying to prove. And then up here it said to prove CD is equal to 6. That should always be your last statement. Whatever you're trying to prove should end up being your last statement. Okay, 5.2, beginning proofs about angles. So I'm going to start in the upper left side. So when writing proofs, your reasons will often come from postulates, theorems, properties, and definitions. We talked about that in 5.1. And then, like I said, it's helpful to kind of create a list every time you see like a new postulate, a new theorem, anything, add it to your list so that you can refer back to it. And we can also write reasons using conditional statements, which were from a previous lesson. Conditional statements were the ones that were in the form if P, then Q. Like our example was, if you take me to a movie, then I'll buy you popcorn. That was a conditional statement, and we can use those in our reasons column also. So when you use a conditional statement, this part's really important. So like in your notes, I would box it or highlight it or something to make it stick out. So whenever you're using a conditional statement, the hypothesis of the statement has to be related to the previous statement in the proof, and the conclusion needs to match the statement that the reason is supporting. So we have this example on the right side, this like little kind of mini proof box or part of a proof. So in this problem, we're given that angle A is a right angle. So that's step one. And then my next statement is claiming that the measure of angle A is equal to 90 degrees. And my reason is a conditional statement. It's an if-then statement. So over here, it says that the hypothesis must be related to a previous statement. So in this case, my hypothesis, P, is this if an angle is a right angle. And that was the same, or it was related to my previous statement. And then over here back to the left, it says the conclusion needs to match the statement that the reason is supporting. So my conclusion, Q, is it has a measure of 90 degrees, and that's the same thing as the statement that I'm trying to make. So I would like save this, keep it somewhere where you can refer back to it because that'll really come in handy. And then just remember for if-then statements or conditional statements, the hypothesis is P, and then the conclusion is Q. Those are the variables we use to represent them. Okay, so for our example, we're going to use a two-column proof to prove the linear pair postulate. So the linear pair postulate says, if two angles form a linear pair, then they are supplementary angles. And if you don't remember what a linear pair is or a supplementary angle, it's not a big deal. I have them defined down below. So a linear pair is a pair of adjacent angles, meaning angles that are side by side, whose non-common sides form a straight angle, which is essentially a straight line. And then supplementary angles, it's a pair of angles whose measures have a sum or they add up to 180 degrees. So before we get into like our proof, I kind of want to draw like a diagram of what the linear pair postulate is saying, just to help me kind of wrap my head around it. So I'm going to first draw a linear pair. So it says that they have two adjacent angles whose non-common sides form a straight angle. So let's say I have an angle right here, and then my adjacent angle would be sharing the same side as it, so it would still have like this side, and the non-common side would form a straight angle, so it would extend over here. So adjacent angles, they share a side, they're like side by side, and then their non-shared sides, so this one and this one together form a straight angle. So that would be a linear pair. And of course, it could be like arranged a little bit differently, but it should kind of look the same no matter what. I'm just going to straighten out this line. And then the second part of that postulate says, then they are supplementary angles. And if you know what supplementary angles, you're probably looking at this picture, you're like, well, duh, yeah, they are. They're adding up to 180 degrees, which is a straight line, but we have to prove that. So that's a lot of proofs in general, is kind of proving what feels like common sense after you've learned it for the first time. So I'm going to go ahead and I'm going to start labeling my diagram. So I'm going to say this is angle 1, and then I'm going to call this angle 2, and then I'm going to give myself some points on it. So this will be A, this will be B, this will be C, and then point D will be up there. Okay, so before we jump into the given and the prove, we have one more thing to do. I kind of just want to identify, okay, what's the hypothesis and what's the conclusion from this statement, because this postulate, I'm going to erase some of this clutter so it's not too overwhelming. This statement right here, if two angles form a linear pair, then they are supplementary angles. That's an if-then statement. It's a conditional statement. So remember, the if and the then are kind of a part of the form of the statement. And then the hypothesis is that first part. So two angles form a linear pair. That's my hypothesis P. And then the angles being supplementary angles, that's my conclusion Q. So my hypothesis is going to be what's given. And then my kind of what I'm trying to prove is my conclusion. So for given, it's going to be my hypothesis P. For what I'm trying to prove, it's going to be my conclusion Q. So I don't want to just like, for my given, right, like the very general two angles. I want to actually be able to describe those two angles. That's part of the reason that we drew the diagram. So the two angles are angle 1 and angle 2. So we're going to say given angle 1 and angle 2, and from the hypothesis, we were given that they form a linear pair. So angle 1 and angle 2 form a linear pair. And then we're trying to prove our conclusion that they're supplementary angles. So we're trying to prove that angle 1 and angle 2 are supplementary angles. Okay, so we have our given information, and then we have kind of where we're trying to end up, which is that supplementary angles part. So for our first statement, we're just stating what we were given. So angle 1 and angle 2 form a linear pair. And then for reason 1 is that that information was given to us. It was just kind of given to us in combination by what our hypothesis was, the two angles form a linear pair, and the diagram, and the diagram that we drew for it, where we kind of labeled everything. And if you had labeled differently, the gist is still the same. So if you said it was like angle 3 and angle 4, you would just replace those numbers. Okay, so the next thing that we can pull from all this information, it's going to help us lead to our end goal, is the fact that we know, like by definition, that linear pairs form a straight angle. So we can say that the angle formed by our linear pairs is a straight angle. So the angle formed by our linear pairs is A, B, D. So we can say, or sorry, A, B, C, excuse me. We can say angle A, B, C is a straight angle. That's not how you spell straight. I forgot my R. Sorry. Is a straight angle. Okay, and then the reason is going to be just kind of like a summary of the definition of a linear pair. So we can say if two angles are a linear pair, then they form a straight angle. And that just came directly from our definition of a linear pair, which is up here. It's highlighted in yellow right now. So linear pair is a pair of adjacent angles whose non-common sides form a straight angle. So we said that angle ABC was a straight angle, and then our reason was if two angles are a linear pair, then they form a straight angle. So just basically rewrote the definition. Okay, and then next we can kind of go into what we know about a straight angle. So a straight angle is essentially like a straight line, which we know the degree measurement for a straight line is 180 degrees. So our next statement could be angle, or the measure of angle ABC is equal to 180 degrees. And then our reason is just going to be the definition of a straight angle, which is if an angle is a straight angle, then it has a measure of 180 degrees. So if a measure, oops, no, sorry, not if a measure, if an angle is a straight angle, then it has a measure of 180 degrees. And that's just another by definition. So the definition of a straight angle is an angle that measures 180 degrees, because basically like a line that goes straight across. So if it's a straight line, it's opening at 180 degrees. And then next we can use something called the angle addition postulate, where we know that if we take like kind of two smaller angles and we add them together, we get the bigger angle. So we don't really know the angle measurements of our smaller angles, so like angle 1 or angle 2, but we know that if we add them together, we get our straight angle, that entire thing. So we know that's a measure of ABC, so we're going to state that next. So the measure of angle 1 plus the measure of angle 2, so the two individual measurements, so right here plus right here, if I add those together, I get the entire angle measurement, which is the measure of angle ABC. So equals the measure of angle ABC. And that's like our, I guess, justification for that one. It's called the angle addition postulate. And again, like you're not really supposed to, I don't expect you to have these memorized, but this is where it would come in handy to have like a list of each postulate and like rule and kind of what it means. So the angle addition postulate is like if we take two smaller angles and add them together, if they're adjacent, we get the combination angle. And then between step 3 and step 4, okay, so we knew that the measure of angle ABC was 180 degrees. So now we can take that 180 degrees and substitute it in for the measure of angle ABC and rewrite it that way. So our next statement is going to be the measure of angle 1 plus the measure of angle 2 is equal to, instead of the measure of angle ABC, like using the angle addition postulate, we can substitute that 180 degrees in to get the measure of angle 1 plus the measure of angle 2 equals 180 degrees. And that's called the substitution property of equality, where we substitute one thing in for another, assuming that they're equal. So substitution property of equality, and this one was at the beginning of this notes. It was in that box up above. I'll zoom out really quick. So substitution property of equality was all the way up here. So if A is equal to B, then A can be substituted into B for any equation. So down here we're saying that 180 is equal to, or sorry, the measure of angle ABC is equal to 180 degrees. So that means I can take that 180 degrees and substitute it in for the measure of angle ABC. And then the definition of supplementary angles back up at the top is that it's a pair of angles whose measures have a sum of 180 degrees. And that's what we just proved. We proved that the measure of angle 1 plus the measure of angle 2 is equal to 180 degrees. So we can stop there because we got to the point that we were trying to prove. We're trying to prove that they're supplementary angles, which by definition just means they add up to 180 degrees. Okay, this was one kind of walkthrough example from the 5.2 workbook. There's one more though that I would suggest going through just to kind of get another like practice with proofs. I don't want to make this like an hour-long video for you guys, but I would definitely practice that before you go through the assessment part of the workbooks.